up to 5.6. 5.7 is a short section. It's just the last topic. So we already showed that the unitary transformation, they preserve the scalar product, but now we transform both the vector and the operator using the unitary transformation to transform to different bases. Now it's just to show that in different bases, the equations are the same. And the equation now is you have operator A. But now this equation actually is writing in like already a matrix form. So you have in terms of certain matrix, the operator A has matrix A and a state, the operator, the state, which is now a vector. You write the vector notation. This is like a matrix, and this is like a column vector. And that will give you a column vector, right? And now we transform everything into another basis using a unitary transformation. Then we're expecting to get this will give you in the new basis. If you transform everything according to what we did, then it should give you the same form of the equation. So that's so this is some kind of invariant, although in some cases we call this preserving the form of equation. We call it a covariant, but that's fine, just terminology. But now we transform from B to B pi using the U. So U dot B. Let's just simplify the notation. U dot B. Now A pi is transformed from A using the U A and U deck there because it's unitary. So we transform like that, and now you have C pi is transformed like U times C plus C. Right. And then obviously the U deck is U inverse because it's unitary. So this multiply will be identity matrix. So this is U A C, right? And to get the original form, you multiply by U inverse. So multiply by U inverse, which is just the U decker. Then you get back the A dot C. So, which is very simple, very straightforward. So that's one property. It preserves the equation, the form of the equation. And the second one is it also preserves the expectation value. So the next one, so we have again an operator, but then you have psi, you have a state psi or vector, which has component by I using the coefficients of I, right? And now this state you can operate, right? You can sandwich it. You get what we call the expectation value, right? And then obviously if you get everything into basis, right? This is psi just given by this one. A is given by the matrix A with a matrix element A, this little a I j, right? Then where we can do it in abstract way. So this is this A. This A is operator, but if it is also expressed in the same basis, we can write like a matrix. So this will be by the coefficient. It's just matrix multiplication now. It's C deck, which is just the transpose in complex conjugate of C. So this C originally is a column vector. This becomes a row vector, and then dot into the matrix A, and then dot into C. So that is the expectation value in terms of this the basis, this basis 5. So we already mentioned that this matrix A, what we call the mu component is just y nu A y mu. Right, this is what we defined before. Using this and then the expansion of psi, then you can calculate this expectation value, just like a matrix multiplication like that. Right, and now the idea is that this, if you change the basis, then obviously change the coefficient also. Also this matrix element will change, but then the value will not be changed, because if you have in a new basis, so that the psi is equals to I C prime I by I prime, and then obviously A is this new mu prime becomes you can say this is new mu pi is given by phi mu pi A by mu pi. Right? So that's in the new basis you have a new vector C sub I, and then the matrix A with the matrix element mu mu. And the relation between this and that is the Ci prime. So using this, obviously you calculate this expectation value using this new basis. Obviously is C prime deck dot A prime dot C prime, right? Just like what we did before. But then the relationship between C deck and C is just U dot C C deck. This is the prime, and then A is just U A dot U vector, and then C prime is again U dot C. Right. And then we use the property as this is transpose complex conjugate, right? So we can use the property that this is like the C transpose dot into U transpose. Right? That's just how you do the transpose of this product. This is originally a square matrix dot into the column vector, but if you take the transpose of that, it's the same as this row vector, and then which is a transpose of C, and then a dot into the U dagger, right? And that's just a property of how you matrix manipulation, and then dot into U, and dot into A, dot into U dagger, and U C. Now U dagger is just U inverse. All these are these multiplications are identity matrix. So this just back here. Dot A, dot C. So the expectation value is not dependent on the choice of the basis, which is obviously the required result, because basis, you are just using the basis to represent the same function, same vector. So whatever basis you use, you should get the same expectation value. Right, and it's okay up here. Right. Now there are two more invariants mentioned in this section. So let's go back to here. And one is this, the trace of a matrix element. It's invariant. The trace for a matrix is just sum over all the diagonal terms. Sum over all the diagonal terms is the trace, right? So if you have a trace of the A prime in this calculation, you have this A prime, which is a matrix. It's this U, A, U deca, just transform from the matrix A by this unitary transformation. Now we calculate the trace of A, trace of A prime. No, it's just substitute this into here. It's just trace of U, A, U deca, which in this case is just inverse. Right. Now you can write this in component form to make it explicit. The trace is basically sum over all the diagonal elements. So it's whatever the diagonal terms, so whatever the mu new terms, sum over all the new and new terms. But then this matrix, this summation, you can write it like so you have a U. I think that's for your textbook. U new mu, and this multiplied by A mu. In your textbook using little A nu tau, and U inverse tau, and suppose that you are summing over nu and sum over tau. So the last index should be another arbitrary index, but then you sum over trade, meaning sum over the same matrix element, the diagonal term. So it's nu and nu, and sum over nu. Yep. Actually, you sum over nu, but then you also sum over mu and tau. What we do is the sum over tau and sum over mu. Sum over mu, sum over tau, and take the sum over nu here, and then U inverse tau, mu, mu. Just basically rearranging all these factors, but then identify this is the matrix multiplication of U inverse and U, which will give you a conical delta, which is this is an identity matrix, or you can say this is delta tau mu, mu tau. And you can sum over one of them, sum over tau, and sum over mu, and A tau, mu. So this is the trace of A. Okay. That's just straightforward to show that the trace is invariant upon this unitary transformation. Okay. And okay, follow that. stop me and you can look for it. Yeah. Yeah.
Like when you're talking about tracing a matrix, what is that like producing for you like physically?
A trace is just a term, just basically you have a matrix like you have 3 by 3 matrix A11, A12, A13, A1, A2, A3, A1, A2, A3. You have matrix like that. The trace is nothing but just adding up all the diagonal terms. It's just A11, A22, A33, and that generally to any dimension. It's just sum over all the diagonal terms. It's called a trace. And later on we'll have some mathematical property. I think with something mentioned in earlier chapter, I think chapter 2 or chapter 3 that will be proved in chapter 6, right? Involving the trace and determinants. So there is some special mathematical properties like this invariant to make this a interesting quantity because it is invariant upon transformation, this unitary transformation, and so that is make it a special quantity. Okay, but it's just by definition it's just this sum of diagonal elements. Okay, and now the other where quantity that is preserved is our invariant is this determinant, which is even more straightforward. So like using the same A, the determinant of A prime is this determinant of this part UA and U inverse, or U dagger is just U inverse, right? And that by the way you take the determinant, if you have product of square matrices, this is like the determinant of U multiplied by determinant of A multiplied by determinant of U inverse. But then, because now after you take the determinant, these are just number. Now the order doesn't matter. You can group these two together first, and then do the same thing backward. So you can say this is equals to the determinant U inverse A. Right? So reverse this order of these two, and then going back one step, the determinant of this one. And now U and U inverse is just one identity matrix, which is determinant of A. Right? So also the determinant is invariant, and then that's the property. And I don't think I mentioned that before, but the determinant of a unitary matrix is actually because U inverse and U is this U dagger U, right, for a unitary matrix. And if you take the determinant of that, obviously this is just one, right? Because this is just identity matrix, determinant is one. And then use the same theorem. This is determinants of U dagger and determinant of U. But then the dagger is just transpose and complex conjugate. And the determinant of a transpose is the same as the determinant of the original matrix. So this is just like determinant U complex conjugate times determinant of U. Right? So the determinant of U, the complex magnitude square is this is complex magnitude square is just one. Right? And then you can say that the determinant of U, this means that the determinant of U is some kind of a phase, e to the I phase, something like that, the real phase, right? Because that will give you the the determinant magnitude is equals to 1, right? Because right, this is e to the I theta multiply complex quantity e to the minus I theta, and the two product will give you 1, right? Yeah, that's this property. So but that's another property of the unitary matrix. And I guess that's all here. Or section 7. Section 8 is just nothing but a summary, so I don't need to go through that. You can refer that when needed. So but that's it for chapter 5. Any question so far? Chapter 5 is okay.